All right, today we're going to tear down something you've probably seen 1,000 times but never really looked at, the industrial conveyor roller. I mean, on the surface, it's just a spinning steel tube, right? So simple. But what's hidden inside is this incredible engineering battle. A battle that decides if this thing's going to last for years or just completely give up the ghost in a few months.
And that right there, that's the big mystery we're tackling. Think about it. In a massive operation, a mine, a port, a cement plant, when a conveyor goes down, we're talking thousands, maybe tens of thousands of dollars an hour lost. Just poof. So how is it that one roller can spin away happily for years, while its twin, looking exactly the same, just seizes up after a few months? The stakes are unbelievably high, and let me tell you, the answer is a lot deeper than you'd expect.
Well, the secret really boils down to a classic dilemma, doesn't it? It's the sticker price versus the real price. You can focus on the lowest initial cost to save a buck today, or you can think about the total cost of ownership, what that part is actually going to cost you over its entire life. That cheaper roller, yeah, it looks good on the initial purchase order, but its true cost? Oh, that shows up later, in all the replacements, the labor hours, and the killer downtime.
So, to really get why this happens, we have to go undercover. We need to look right past that steel shell and into the guts of the roller. We're going to investigate what I call the 3 silent killers. These are the invisible forces that are destroying these things from the inside out, making them fail way before they should.
And here's our lineup of culprits: contamination, vibration, and bearing fatigue. Now, each one of these is its own unique engineering headache. And you guessed it, a cheap roller? It pretty much fails to deal with any of them. So let's break them down one by one. Okay, first up, contamination. And get this, it's responsible for a whopping 70% of all roller failures. 70%! In super dusty places like a mine or a cement plant, you've got all these tiny particles just sneaking their way past cheap seals. And what happens next is nasty. They mix with the grease inside the bearing and turn it into this abrasive grinding paste. It literally eats the bearing alive from the inside.
Our second silent killer is vibration, and this is caused by something called total indicator runout, or TIR for short. All that really means is it's a wobble. See, a poorly made roller isn't perfectly round or centered, so as it spins, it creates this constant hammering effect, whack, 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 with every single rotation. Now, it's a tiny impact, sure, but multiply that by thousands of spins a minute, 24/7, and you get catastrophic metal fatigue. And the numbers here really tell the story. A standard off-the-shelf ruler might have a wobble, a TIR of up to 2 millimeters. But a precision-engineered one, it slashes that to less than 0.8 millimeters. That's less than half. That huge reduction in wobble is what directly kills that destructive hammering effect we were just talking about.
Okay, so we've seen the problems, we've met the silent killers. Pretty grim, right? But now for the good part. Let's flip this around and look at the solutions. We're going to get into the specific design choices that smart manufacturers make to fight back and actually engineer a roller for a long life. So to beat contamination, the #1 enemy, you need a way better seal. Your standard roller, it just uses a simple little single lip seal, which, it wears out, it gives up, it fails. The engineered approach is way cooler. It uses a multi-stage labyrinth seal. Think of it like a complex maze that uses the roller's own spinning motion, centrifugal force, to literally fling dust out and away from the bearing. It's not a passive wall, it's an active defense system. And to get rid of that killer vibration, well, that comes down to pure precision. Instead of just grabbing some standard piping, an engineered roller is built from a precision tube, which means it has a perfect uniform wall thickness for way better balance. The shaft isn't just roughly turned on a lathe, it's meticulously ground down to a super smooth, incredibly precise finish. It's all these little details that add up to get that ultra-low TIR, and that's how you kill the hammering effect right at the source. And finally, we've got to protect the heart of the whole operation, the bearing itself. An engineered roller isn't going to use some generic, no-name brand. It's going to use a premium one. It also specifies what's called C3 internal clearance. All that means is it gives the little parts inside the bearing more room to expand as they get hot from running all day so they don't seize up. A standard bearing doesn't have that. And maybe most important of all, the bearing is pressed into its housing with what's called an interference fit. It's super tight. That means it can't spin around in there and destroy itself, which is a super common way for cheap rollers to fail.
All right, so we've completely dissected a single roller. Now let's zoom out, because of course a single roller doesn't work alone. It's just one small part of a massive system. And to make sure a system that big is reliable, the entire industry has to be on the same page, speaking the same language. And that common language is called CEMA. It stands for the Conveyor Equipment Manufacturers Association. You can just think of it as the official rulebook for the industry. It's what makes sure that, say, a CEMA C-class roller from one company can handle the exact same load as a CEMA C from a totally different company. It covers everything from shaft size to bearing life, and it's what lets engineers design these enormous systems without just guessing.
Now, this chart shows a really key CEMA principle in action. It's called the deflection penalty. So look here, a CEMA C-roller on a pretty narrow 36-inch belt can handle 900 pounds, no problem. But take that exact same roller and put it on a much wider 60-inch belt. Suddenly, its load rating drops to just 700 pounds. Why? Well, because the longer shaft bends or deflects more under the same load, and to stop that bending from wrecking the bearings, you have to lighten the load. It's a perfect example of how the tiny details of one component are tied to the design of the entire system.
Okay, we've gone deep. We've covered the silent killers, we've looked at the smart engineering solutions, and we've talked about the industry standards. Now it's time to bring it all home. Let's connect all these technical details back to where we started, the bottom line, the money.
And just so you know, this isn't some niche boutique concept we're talking about. A top-tier manufacturer that's all in on these engineering principles, they're cranking out over 4,000 of these high-spec rollers every single day. This is a proven high-volume philosophy that's all about driving reliability on a massive scale. And here it is, the final payoff, the total cost of ownership. So yes, look at the initial cost. The engineered rollers are more expensive upfront, no doubt. But then, look at the replacement costs. The standard roller ends up costing more than double per unit over its life, 6,000 rupees compared to just 2,420. Once you factor in all the replacements, the labor, the downtime, it's not even close. That upfront investment in good engineering, it pays for itself over and over and over again. And that really brings us to the big takeaway here. We've just peeled back the layers on a supposedly simple part, a conveyor roller, and found this whole complex world of engineering hidden inside. It really makes you wonder, doesn't it? What other simple components in your own plant, in your operation, deserve a second look? What other parts are out there, silently costing you a fortune? What happens when you finally look past that sticker price and start asking about the true total cost of failure?